In this video, we are going to understand the concepts of broken functional level authorization and broken object level authorization, how they differ from each other, why these vulnerabilities are dangerous, how they commonly occur in backend applications due to developer mistakes, and how to properly fix and prevent them. To understand the concepts better, I have created a practice-based backend system to understand these vulnerabilities better. I have provided the full GitHub repository link for this project in the description. You can run this backend application locally on your machine and test on your own. First, let's quickly recap what authorization means. Authorization is the process of verifying what actions or resources an authenticated user is allowed to access. For example, only users with admin role should be able to access admin pages and perform admin-only actions, while normal users should not have access to those functionalities. Now let's look at some very dangerous vulnerabilities related to authorization, how they commonly happens in backend systems and how attackers can exploit them. Broken functional level authorization. Broken functional level authorization happens when a user is able to access backend functions or actions they should not be allowed to use. For example, imagine a normal user accessing admin-only APIs like deleting users or view sensitive admin data. Another common case is accessing hidden or internal endpoints directly. Even if front-end hides these features, attackers can still call these API manually using tools like Postman or Bug Suite on the backend. These vulnerabilities are very dangerous and are ranked in the API security top 10 by OWASP. Let's try to understand this with example. Here we have a route or API endpoint that is used to fetch all user records from the database. In our system, we want only users with the admin role to be able to access these routes. But there is a missing authorization check here. In this route, the application only uses the verified token middleware. This means the backend only verifies that user is authenticated, but not verifying whether the user actually has admin privileges. Any login user can now access this admin-only endpoint and retrieve all the user's information from the system. To properly secure the route, we add the isAdmin middleware here. This is a custom middleware function and you can name this function anything. The isAdmin middleware verifies whether the authenticated user has the required admin role by validating the role value from the logged in user session. We already covered how this middleware works in the previous videos. Now the backend checks both: is the user authenticated and does the user actually have admin privileges. Here we have another example of broken functional level authorization. Sometimes developers may forget to add authorization check on newly created routes in the system. Missing this authorization check is one way of broken functional level authorization vulnerabilities. Here the update route is protected with isAdmin middleware, so only admin user can update grades. But the delete route is missing an authorization check and only verifies authentication. So while one method on the route is properly protected, another method on the same route is left exposed. Front-end only authorization checks, hard-coded role logics on the backend are some of the common reasons broken functional level authorization vulnerabilities happen in real-world applications. Later in this series, we will see how to implement a secure authorization mechanism in our system. Now let's look at another very common and dangerous authorization vulnerability called BOLA, which stands for Broken Object-Level Authorization. BOLA happens when a user is able to access or modify resources that do not belong to them. For example, on a functional level, all the users in the system are allowed to view records in the system like chat messages, orders, invoices, or enrollment records. But what if some user might be able to view someone else's records by exploiting the vulnerability? Similarly, they could even edit or delete another user's data. This is a critical security issue because the system fails to properly restrict access at the object or resource level. This vulnerability is very dangerous and it is ranked at the number 1 by OWASP in the list of top 10 API security risks. Let's understand this with example. Here we have getEnrollmentById function in our demo application. This function is used by student users to fetch a user's own specific course enrollment record. A student user must not allow to view what courses other students are enrolled in. But there is a security problem here. In this function, we are directly taking the enrollment ID from the API request and passing it into the database SQL query without verifying whether the enrollment with that ID actually belongs to the currently logged in user. This means an attacker can simply change the ID in the request URL and access another user enrollment record. For example, an attacker can try different enrollment IDs in the request and potentially access all enrollment records belonging to other student users in the system. If the backend does not verify ownership, user can access records that do not belong to them. We must ensure that user can only access their own enrollment records, not other user records. So how can we do that? We can solve this by adding a resource ownership check. Let's understand how this works. Whenever a new resource or record is created, such as course enrollment orders or chat messages, the backend also stores the ID of the user who created that resource. Later, when the user tries to access that private resource, the backend compares the user ID stored in that record with the ID of currently authenticated login user. If both IDs match, access is allowed. If they don't match, the request is denied. Now let's see how can we add this ownership check in our code. The ID variable contains the enrollment ID from the client-side API request, but the important part is the user ID. The user ID comes from the request.user.id parameter, which is extracted from the authenticated JWT token inside the verified token middleware. This user ID value comes from the login user session and is the user ID of the currently logging user. This means the attacker cannot manually change or control this value because it is taken from the authenticated user session, not from the request body or URL. We then use this user ID in our database query and compares it with the student ID or user ID stored in the enrollment record. So now the query only returns a record if the enrollment ID exists and the enrollment belongs to the currently logged user. If the IDs do not match, the query returns no result and access is denied. As a result, users can only access their own enrollment records and not other users' private data. This ownership validation is one of the most important techniques for preventing broken object-level access control vulnerabilities. Also ensures when accessing users' own provided resources, always take the user ID from the authenticated user session or JWT token, not from the client control input like the API request body or URL, because attacker can manipulate those values. In the upcoming videos, we will design a upgraded RABEX system in a secure way within our demo project to protect against broken object level authorization and broken functional level authorization vulnerabilities. If you want to stay updated with the Authorization Security for Developers series, make sure to subscribe to the channel so you do not miss the upcoming videos.